Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Andrew Bretz. Andrew is a thermal and CFD engineer at Thermal Analytics, where he works on thermal modeling primarily for automotive applications. He works in spaces from 1D system modeling to 3D full vehicle modeling with a focus on vehicle cabin and HVAC modeling. He also works with the engineering team to develop innovative software coupling solutions. Andrew has a BS in Mechanical Engineering from Michigan Technological University and has been with the TAI family since 2021. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. And we are also recording this webinar and we'll be sending you the link following this presentation. And with that, Andrew, if you're ready, you may begin.
Yeah, so today we're going to be talking about process automation for human-centered design. Basically, because the world is going to a more virtual space, we want to try to make everything as automated and as simple to set up as possible, minimizing user inputs. So that way we can be more efficient when we're designing our human-centered cabins and focus more on the results and less on the setup. So for a quick agenda, I'm going to go into an introduction of the topic, and then like why we need to focus on human-centered design and automation, and then some simulation methodology and a simple process that I've prepared to go through a automated human setup, and then a quick case study and with the model setup and results of that case study. And then some conclusions on benefits of using an automated system to set up a human design. The case study I'm going to be going into today is going to be focused on a radiant panel study, which is a common automotive application where we're focusing on heated panels near occupants to improve comfort and sensation. And how we can go through a simple design sweep with this process setup for the radiant panel study. Okay, so a quick introduction on the topic. The market trend for virtual prototyping is driving the need for predictive cabin simulation. So the automotive simulation and analysis market is expanding every year, and OEMs are trending towards virtual prototyping and numerical simulation instead of the standard testing environment. So we want to try to do virtual testing to save money, get results faster, and avoid the expenses in hands-on building and prototyping. So for example, the design and concept for the 2021 VW shown on the screen was completed 100% virtually. And this is to reduce cost and time to market. So we're trying to adapt to that space and create virtual environments that are easy to set up and execute our simulations to ease this prototyping in the virtual space. So a process I'm going to be sharing with you today is built in our CoTherm software. So as a quick introduction to CoTherm, CoTherm is our software that enables multi-physics CAE simulation, primarily focused on co-simulation, design optimization, design analysis, and automation. And today we're going to be focusing on the automation section, where we have CoTherm automatically prepare and then run and then post-process our simulation. So CoTherm has two stages to it, essentially. The development of our CoTherm process, which we'll be developing based off a template, and then we can do a handoff to an analyst that will be able to actually execute the runs, and it'll go through an automated process of this initialization, simulation, and post-processing. And we can continue to loop through that based on our design requirements. In this example I'm going to be sharing today, we're going to also be using TAITherm, which is our comprehensive thermal solver that works in all bands of heat transfer, from conduction and convection to dual band radiation, also considering environmental effects such as solar loading, wind, and then different terrain effects. TAITherm also has the ability to use TDFIO-Pi, which is a Python scripting interface to edit the TAITherm variables. So you can edit your boundary conditions, your run setup, and everything through TDFIO-Pi. And finally, we'll be making use of our human thermal extension. So our human thermal extension is an extension to our TAITherm software that focuses on a detailed physiology model that can output comfort and sensation results. So it takes your standard model inputs of, environmental parameters, physical contact, clothing, the human's activity level, any initial conditions, and then it outputs items such as clothing and skin temperatures, core body temperatures, local and whole body heat fluxes, and thermal sensation and comfort. So it's a full thermal extension in regards to the human that considers all of our modes of heat transfer and will output specific human outputs. And while we're talking about Berkeley sensation and comfort, it's good to distinguish the differences between the two. So sensation will be how hot or cold something is perceived to feel, and comfort is whether that sensation makes the person feel good or bad. So sensation directly corresponds to temperature. So if we have a hot environment, the sensation will be very hot, but that doesn't necessarily mean comfortable or uncomfortable. So even if the human is very comfortable on the comfort scale, we don't know if it's a hot environment or a cold environment. So it's just a good thing to make note of, that there are significant differences between sensation and comfort. So I'm going to go quick into this cabin analysis process that I've put together. And just for some background, basically we're going to be focusing on this loop here. So we start with geometry and a mesh that's already prepared. We'll set up the humans through this process. We'll prepare the cabin through this process by importing our boundary conditions. We'll run the simulation. We'll post-process these results. And then we'll go through the loop again, adjusting some inputs. So this process could restart with new geometry if needed, as long as it's meshed and prepared with the same boundary conditions and same part IDs and stuff like that. We could adjust geometry if we wanted to. So think vent positions or radiant panel size or something like that. We could change that and continue going through the loop. So what this does is this goes through, sets up your entire simulation, runs your entire simulation, and post-processes the simulation and repeats. And this is great for automating our setup, so we don't have to go through and make manual selections of our part types, manual selections of our human setup. So you don't have to manually set up your entire model. So this is the CoTherm process view of this setup. So we have our start block in the top left corner, and from there we move into human setup and initialization. So this prepares our humans to use this human thermal extension. So it'll go through precondition the human, set up your Berkeley set points, and all of that before moving on to setting up the vehicle. So in the vehicle cabin block there, we set up the vehicle by importing our boundary conditions and then run the model. And then after that, we have our post-processing task, which will run your thermal reports and do any post-processing and directory cleanup you need. Then it'll continue running through the table and continue executing runs. So just to dive into this a little more, going into the setup humans subprocess, we see that there's multiple subprocesses here in setting up our humans. So in this example model that I'll be showing, we've got 2 humans, a driver and a passenger. And in this setup, we can define how our human is set up. So in this case, we have a female driver at the 50th percentile for weight and height, and they're in an office clothing ensemble with an activity level of 1.1 Met. Similar story for the passenger, except the passenger is a 75th percentile male, but with the same clothing and activity level. And so we can go through this table and add humans if necessary, remove humans if necessary, depending on your model. And you can go through and change the gender, height and weight percentiles, clothing and activity levels, all through this little table here. And what that will do is it'll set up your human with those values, and then you can go through the process and it will define the physiology of the human and all the area weightings associated with that. They'll define the clothing on the human and basically prepare your human setup dialog for you for this human thermal extension. After that, it'll calculate your Berkeley set points and a reference condition for the humans, and then it'll precondition the humans. So in this loop, it'll go through each human one by one, and you'll have results for those humans in their preconditioning state. Then moving forward, we set up the vehicle cabin. So in this task, we will import our boundary conditions, which that can either be a subset of your boundary conditions if you have a model mostly prepared, or it can be all of the boundary conditions needed for the model. So in the case of our study, it'll just be varying our heated panel heat rates and then running the TAITherm solution. So after that, we'll have to post-process our model. So we'll be able to run our thermal report, and then we can do a directory cleanup and all of this. So because this task is a CoTherm journal, that means it uses a Python script to go through and clean up your directories. And that being said, you can go through this Python script and add anything you want in terms of extra post-processing. So you can add stuff for CoTherm scatter plots if you're interested in that. You can save images of the file with the TDFI extension if you're interested. So there's a lot of options here for your post-processing because this is a Python script and you can add whatever you need to it. Also, for example, like we have a thermal comfort analysis tool that we can add to this that can run from Python and produce PowerPoints based on your human thermal results. So all of that can be done through this journal task because it is just reading a Python file and executing a Python file. So this case study I've been alluding to this entire time is regarding heated surfaces in human comfort. The reason why we're focusing on heated surfaces is because the market is moving towards EVs and the EV range anxiety is a big concern with the adoption of EVs. And the reason is because there's less charging stations out there, so people are a little nervous on where they're going to go charge up their vehicles because they're not as common as gas stations yet. And so part of that involves making sure our systems are as efficient as possible, and that's problem is emphasized in the winter when we're doing cabin heating, because the HVAC system takes up a large amount of your energy in the winter, because you can no longer use waste heat of your combustion engine, and all that heat has to be generated somehow. So OEMs are going towards more creative solutions, such as these radiant panels, which are placed near the passenger and driver for radiative heating. So as shown in the screenshot here, these are heated surfaces that we're going to be focused on. There's going to be a roof level heated panel for each the driver and passenger, and same with one in the footwell. Both the driver and passenger will have a heated seat, and the driver will be holding onto a heated steering wheel. So in this cabin warm-up scenario, it's a 1-hour simulation with a -7°C ambient, and the human precondition is a standard office environment at 20°C for 30 minutes. And so this is our starting thermal model. The vehicle parts and were prepared with typical material properties and surface conditions. And then interior convection was set to an air temperature curve with the standard heat transfer coefficient of 10 watts per meter squared Kelvin. And thermal links are defined between the humans and the vehicle. So the humans are linked to the seat and steering wheel for conduction pathways. So some more setup for the thermal model. The humans are just prepared as geometry at the start of this process. So no clothing is applied, no convection is applied, nothing is in our human setup dialog. So traditionally in our human setup dialog, we'd have to set up a body part map, Berkeley comfort reference state, and a thermal reference state for the human. And all that is done by this process. So it takes some of the manual work out of setting it up. So this animation here is a quick result of an HVAC only version of that simulation. So the heated panels are not active. And you can see that in the seat, specifically where the seat's warming up based on the human warming up, and your convection in the cabin. And then here are some high-level Berkeley sensation and comfort results for the HVAC only case. We have our driver on the left-hand side and our passenger on the right-hand side. And just as a reminder, the passenger is a 75th percentile male and the driver is a 50th percentile female. So there is some different physiology weighting in there. Yeah, so this is the baseline results, and we'll move on to our heated surfaces. So these heated surfaces are the surface, so these graphs represent the surface temperatures of our heated surfaces. So as you can see with all of the surfaces, they reach approximately 30 degrees Celsius by 10 minutes. And with these plots here, we basically want to make sure that we're not creating an unsafe condition for the human. So we want to make sure those surface temperatures are below 43 degrees C, which they are for the entire simulation, which means they're safe touch temperatures for the humans. And then this animation here is with the heated surfaces, and you can see right away that the roof panels, the steering wheel, and the seats all heat up quickly to help the human warm up. And then here's our Berkeley comfort and sensation results for these results. And you can see right away that there's a little bit of a jump forward in time for our comfort and sensation results. And those are shown specifically here. So you can see with the heated surfaces, the dashed lines, they occur, the jump in sensation and comfort occurs earlier in the run, and that's just the effects of our heated surfaces. So some conclusions based on this is that our CoTherm process allows users to automate A to B design studies from model setup to post-processing. This is primarily done through CoTherm journals to allow users to customize different variables within CoTherm and any of the external tools. And TAITherm utilizes the TFIO tool to customize the model parameters with the Python script. So the human setup was all done through TDFIO and yeah, all that's done through the journaling. Yeah, any questions, comments, concerns?
All right, thank you, Andrew. Let's go on to some questions here. How is the body part map assigned for each human?
So the body part map is assigned for each human through a dialog in CoTherm. Yeah, I'm not gonna jump back all the way to the CoTherm slide. But anyways, so one of our key properties in CoTherm is a user-defined selection, which you select an assembly in your model to represent the driver. And then say the driver has their individual body parted out. So you have your hands and arms and everything like that. So it goes through that assembly and does a keyword search for, you know, hands, legs, arms, and then assigns those to the body part map accordingly.
All right, thank you. How long did it take for this process to run?
So this process ran on my laptop in just under 3 hours for running the 2 cases, all the Berkeley set points, and all the human setup was all running under 3 hours on 8 cores on my laptop. And the real time savings here is in the setup. So the run times are going to be similar between the process and running it manually, but the savings is primarily focused on the setup. I don't have to go through and set up curves for the heat rates. I don't need to go through and manually set up the humans. This is all done for me through this process.
All right, thank you. Next question. How do you change the preconditioning environment for the humans?
So in this CoTherm process, there are a couple of key properties that correspond to a preconditioning temperature and a preconditioning relative humidity. So that sets your preconditioning environment. So in this case, I set it to 20 degrees C and I think 45% relative humidity. But those are just a couple of key properties in this process that you can change to alter your preconditioning.
All right, well, looks like that's it for questions. So that will complete today's webinar. We appreciate you all for attending. You will receive a follow-up email containing links to download the presentation slides and watch the recorded webinar session. Again, thank you, Andrew, and everyone have a nice day.
Thank you.